Hi, it's Terry Denery of the MathWorks. So in this fourth video, we're going to continue where we left off in the previous one. In the previous one, I kind of went to this effort to be associating names with these little blocks that really aren't doing anything yet other than really just kind of holding a place for the real equipment. In real life, going from this reservoir to this one, although we'll kind of start losing terms like reservoir, but a fluid state here to a fluid state here, that the fluid is receiving heat through an evaporator. And then as we move from this fluid state to this fluid state, we will add pressure to it to essentially drive the flow. So anyways, as we do this, we'll kind of see the equipment that takes place and really the physical phenomena that really drives these things to occur. So anyways, an evaporator. Right, and so let's bring up our browser for Simulink. Okay, it is really a heat exchanger, and it's going to take heat externally and inject it into the evaporator and essentially raise the enthalpy of the fluid. All right, so let's go to Foundation Library, thermodynamics, two-phase fluid elements, and we're going to get a pipe. Okay, let's delete this. Put this in. Connect B right here. And let's connect A right there. All right. So this is a fluid pipe. It's defined by its length, its cross-sectional area, hydraulic diameter. All this will really kind of determine how much flow can move through it. It's got some initialization, which we will probably return to in a little bit. The idea of charging your refrigeration unit with the right amount of refrigerant as well as the right state. It'll all take place through this. Okay, so A and B are flow ports. This H is a thermal port, and it's through this port that we will set up our heat transfer. And our heat transfer is basically going to be conduction, right? And so let me rotate this, and I think I'll set it up this way. Now, heat conduction is pretty symmetric to the two sides that are transferring heat, but and we'll kind of get into that in a moment. All right. Well, actually, let's double click on it. So here's the block. Surface area, thickness, these will be important things. The material properties, thermal conductivity being the most important. And, where's all this coming from? I love hitting on these question marks, which connect us to the help. And through here, you'll see the ultimate formulation that's being applied. And so we basically are connecting two objects. You'll see the block image right there. There's something kind of, I'd say, physical, like fluid on one side, and maybe on the other side something that's solid. But either, again, it's got symmetry, so you're not constrained to which side the pipes can be on in any case. So anyways, but in the function here, you'll see essentially the temperatures of the two states. The difference between the two will be the ultimate driver of the heat flow, and that the thermal conductivity K, the area, and then the thickness are shown here, and how they fit into that formulation. So anyways, I think that's pretty close to what I wanted to say. Let's go ahead and define the nature of this conduction. We'll put a much larger unit, 1 square meter of area for the heat to flow through. And so the bigger, the more heat that will take place. And then the narrower the thickness of the heat conduction path, the faster it will be too. And so in this case, I'm kind of thinking of like a heat exchanger, and I generally think of like tubes, and maybe there are lots of tubes, right? But the idea that the length, and we know that the pipe itself is 5 meters long. If I have tubes, it'll be that 5 meters times the 2 pi r being the radius of the tube, okay? And if I have like 10 of them, then I'd multiply that number by 10. But that ultimate flow area, or let's call it surface area, between the fluid and what it's going to be conveying heat to. I think of it as the pipes themselves have a heat exchanger. So I'm going to put in 1. And then the thickness of the pipe is basically what I'm putting in here, and you'll see I'm putting in 3 millimeters. All right. Now, that heat has to come from somewhere, and certainly there is a T sub A that's driving the heat transfer. And so that's going to basically be a source of heat. And I'm going to think of it this way, that any old mass, presuming it's not operating at 0 Kelvin, contains heat. It contains energy, thermal energy. And so anyways, to kind of keep things simple, we're going to do what I call a solid to two-phase flow heat transfer rule, right? And that I think for this example, let's make sure I get this right, but we're going to be adding heat into the pipe. The pipe is operating somewhere, let's say around 270 Kelvin. And so let's make it considerably warmer than that. So we'll put it in at 340 Kelvin. And that seems pretty reasonable. Let's hit run. Okay, we got a little bit of change, and we're not exactly there yet. And certainly one of the things, it's funny we get anything at all there, but is what's driving that flow is important to me now too. And, oops. And so I'm going to go to the two-phase fluid, and I'm going to get a mass flow rate source. And I'm going to put in mass flow rate of 0.104, which I know is a number that Aaron uses in the more complete refrigeration cycle model that he put together for the tutorial. So anyways, let's put that in and again, just kind of assess where we are. Okay, so I'm good. I'm kind of happy the model runs. And what I want to do now, though, is really kind of think about, well, what's an evaporator and what's a compressor? And putting this mass flow rate source, to me, I actually practiced this like 4 or 5 times before I really began to think about it. Well, that's itself as a kind of a compressor. And so what I'm going to do is I'm going to rotate that like that. And so instead of pushing the fluid through the pipe, we're going to pull it. Okay, I think this still works. Oh, actually, here's actually a really important piece to this. Okay, is that instead of drawing fluid from a reservoir, we're going to draw it from the pipe. And so the pipe, likewise, is no longer dumping into a reservoir. It's going to be going straight into that. And so let's see how we're doing on this now. And I'm looking at the chart right here. So that's a little bit interesting. 2 things I want to kind of take a look at right now is I do want to look at, as I remove heat from here, has it gotten so cold that it no longer is changing its temperature? And if so, what do we want to do about it? So let's go to thermal sensors, and we'll get a temperature measurement, and we'll operate on this node. We like that node. Basically, the lines between any set of blocks are called nodes with SimScape, no matter if it's thermal, fluid, or whatever, right? And that this is one of those measurements that relies upon a reference, and so our thermal reference will be absolute 0, which is what this block represents, and I'll click that in like that, and let's get a signal, which we will convert to Simulink with units of Kelvin. Let's put in a scope. Let's hit run. And what we'll see is the heat of that block, that thermal mass, gets emptied very rapidly, and that's why we end up with kind of the cycle looking like it does right there, right? so that's a pretty easy fix, which is let's choose a bigger block. And so I think let's try 10. And that's not so bad. And it's not a bad idea, because we calculated it already. Is let's compare the fluid temperature. And that's available on this bus right here. It's coming out of that port right now. Let's compare the fluid temperature with the solid temperature, because I think both will be varying. Okay. And they're definitely getting closer, and we're only running for 10 seconds. And if you are interested, we could go for 100 seconds. And I think we'll end up with that same situation where we're going to drain the block of all the energy it can be used for heat. And let's see. Yeah, and we end up in that same configuration again. But what's kind of cool is you look at this and then you go, of course, the block and the fluid are the same temperature now, right? So anyways, I think I'm pretty happy with this, and I think what I'll do now is some good bookkeeping, right? And I think I'll take all that plus all of this, and I will create a subsystem, all right? And inside the subsystem, let's come up with the appropriate labels. And so that'll be A, this will be B, and for thermal things, we like to use the letter H for it. And otherwise, I'm pretty happy with this, with that. And the last thing I'll do, kind of like B to be on the right. All right, and so that looks good to me. Okay. All right, and now I'll call that my evaporator. Okay. Now similarly, I'm going to do this. And so that mass flow source plus the measurements. Oops, I don't want the tags going into the subsystem. I'll throw that in the subsystem too. And not exactly sure why I called it A, because that's called A. Anyways, I want my A to B sequence to continue to go kind of counterclockwise. And so I'm going to come in here and I will name this one B and this one A. All right, and then let's make B show up on the right side. All right, and with that, I'll rotate the block, control it. Like that. Okay, and this is kind of nice. Notice I can grab that port and move it to that side, and now these signals flow very nicely to the go-to tags. And I'm going to hit run. Just make sure we didn't change anything. I'm running it for 100 seconds, so let's just run it for 10. Oops. Okay, really important point. The job of a system like this is to change the temperature of things, all right? And just like a house, you run the air conditioning unit long enough, you're going to bring the house to the right temperature. So the ability to turn it off actually is very important. And as I kind of indicate, that I'm going to make my case for why you want to do this in Simulant throughout these series of videos. One of them is that Simulant is where you develop controls, and it's exceptional for developing controls. And in that final model, well, it will be the final model, but the model I showed that Aaron produced of the big refrigeration system to begin this series, he has really cool controls that kind of make it work. So we'll revisit that too. And I think, with regard to equipment, well, let's go change the name of this now to compressor. Okay, all right. I think I'll do a few kind of nice things. So let's go format. Let's make the lettering bigger. Let's make it 18. Let's make this the same size as the evaporator as a block. And so we go here and we match the sizes of them. That's not what I wanted. Okay, let's redo that. Oh, actually, here's the way to do it. Control R. Oops. Don't want to do that either. I want to deselect this. Control R. And now match the sizes. Okay, and now Control R back. Okay, perfect. Okay, and let's do the better size lettering there too. And I'll just kind of finish this one pretty simply. Okay, that in a way heat exchangers are heat exchangers, and so in a way we already have the condenser done. Although you'll see as we move back to Aaron's model, there are lots of options on how we could kind of set up I'll say the external element, which is exchanging heat with the fluid. And you'll see he did a really nice example where air will cool the fluid, and that'll be through the condenser. So let's delete that. Let's grab one of these now, and I will flip the block by hitting Control I, and then I will okay, good, got it. Right, and the difference really between our evaporator and our condenser really just kind of comes down to, at least in this example, is what we're exchanging heat with, right? And so I'll take all this and I'll kind of connect into it. So this will be a little bit messier than I prefer, but I'll kind of connect into that. Might as well put a scope on it. So let's get this, and but it's gonna be the temperature of the thing we're connected to, and so we're operating actually up here. It looks like maybe about 310 degrees, and so if we put this at like 270, that should remove heat pretty well. And once again, we put in a real component, then we can get rid of these kind of intermediate thermal or fluid reservoirs, right? And I think this will work. Let's go ahead and hit run. Okay. All right. And in truth, this is not working yet. When I showed this model to Aaron's like, "What are you doing, Terry? This is crazy what you're doing." I think the model I actually showed to him, the evaporator was even operating at like 240 degrees. But Aaron's got a great sense for kind of what's real and what you really need to put in there to get real devices and or real components. Okay, and I'd say there are two things that I look at now that I'm now kind of informed on because I talked to Aaron. All right, and Aaron had a huge problem with the location of this point still being in the two-phase regime. Basically that it's still boiling. So there's no way in the world you're going to send a combination of boiling liquid and vapor into my compressor. You break compressors by doing that. So one of the things he kind of explained to me is you got to move the fluid in your evaporator. You have to evaporate it. It has to be pure gas. And so you need to be on the right side of the I'd call it the boundary to the dome right there. He also kind of explained to me too that you really don't need to be operating kind of right on the edge on your fluid entry here, and in a way you don't. You actually shouldn't be. And so we're going to kind of move this point a little bit more to the middle, and it comes up down to this idea of charging the refrigerant system with the, he uses terms like the correct density of refrigerant. And what that really means is you don't want it pure liquid, you don't want it pure vapor. If it's pure vapor, it's not going to have the ability to I'd say, absorb heat at the rate you're going to need to. But if it's pure liquid, it's not going to have the volume in these perfect kind of like, heat exchangers to expand the fluid as it converts from liquid to vapor to 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 achieve the greater, well, I call it specific volume, but let's call it the lower densities at which the evaporated fluid will take on. So anyways, I'd say that at this point, we're kind of getting through the basic capability of adding enthalpy and pressure to the fluid so we can move around that thermodynamic chart. We'll move into the next video, the next demo, back to kind of the tutorial, and we'll kind of see how real equipment gets kind of sized and represented properly. All right, thank you.